Hello, my dear students, and welcome. Today, we're starting a really important chapter, Unit 6, Electromagnetic Induction. You know, this one idea is basically the reason we have electricity in our homes, all thanks to generators. My promise to you is that I'll explain it so simply, you'll never forget it, and everything we cover will be 100% exam safe. Chalo, let's start.
So, what's our plan for today? First, we'll start with a curious question. Then we'll uncover the big secret of this topic. After that, we'll learn the official rule for your exams, see how it works, find out about common traps so you don't lose marks, and finally, we'll have quick revision points. A nice, clear path, Hannah?
Okay, so first things first. Before we get into any heavy definitions or formulas, let's just spark your curiosity a little bit. I want to start with a question. A very simple but very powerful question.
Just think about it for a second. You have a simple wire, maybe a copper wire, made into a loop. That's it. Can you make a current flow in it without connecting any cell, any battery? Now, I know what you're thinking. No, sir, how is it possible? But the answer is a big yes, and this entire chapter is about how we can do this.
Now, this is where it gets really interesting. You might think, okay, I get it. We must be moving a magnet near the coil or something. But what if I told you you don't need to move anything? Imagine, a magnet and a coil are perfectly still. Or, even better, look here. You have two coils just sitting next to each other. Nothing is moving. And if you just change the current in this first coil, a current will magically appear in the second one. How on earth is this happening? Let's find out.
So what is this magic? How does it all work? Well, the secret is actually a very simple idea. And to make sure you never ever forget it, I have a small analogy that will make it absolutely crystal clear.
I want you to imagine all the free electrons inside a wire. Think of them as cars, just waiting in a long line on a road. And the magnetic field around this wire? That's like the traffic signal. Now, as long as the signal is steady, whether it's red or green, it doesn't matter, the cars are just doing their thing. But the moment the signal changes, let's say from red to green, what happens? All the cars immediately start to move. You see? It's the change in the signal that makes them move. It's the same thing here. It's the change in the magnetic field that gives the signal for the electric charges to start moving, and that moving charge is what we call current.
So this is the most crucial point. Please listen carefully. It is not about having a big, strong magnetic field. You can bring the world's most powerful magnet and just keep it next to a wire. Nothing will happen. Absolutely nothing. The secret ingredient, the magic word for this entire chapter is change. If the magnetic world around the coil is changing, you get a current. If it's steady, you get nothing. It is as simple as that.
All right. Now that you have this core idea, this traffic signal idea, fixed in your mind, let's look at the official textbook definition. This is the one you need to write for your exams. But don't worry, now it will feel very easy. So, this is the line, word for word, from your NCERT textbook. Please, learn it by heart. The phenomenon in which electric current is generated by varying magnetic fields is appropriately called electromagnetic induction. See that word again? Varying? Varying just means changing. This is your perfect one-mark answer.
Now, for our own understanding, let's put that in even simpler words. All it's saying is this. Whenever the magnetic flux connected to a wire changes, a voltage is produced. We call this voltage an EMF, which stands for electromotive force. It's just a fancy name for the push that makes the charges move. So this new term, magnetic flux, what is it? Don't get scared. It's just the technical name for the total amount of magnetic field lines passing through our loop. That's all.
Okay, great. Let's go a little bit deeper now. To really get a feel for this, we're going to break down the whole process into 3 simple, logical steps. And after that, we'll do a tiny example with numbers, just to see it in action.
So, here is how it builds up. Step 1, you have a loop, and a magnetic field is passing through it. We give this a name, magnetic flux. Simple. Step 2, how can you change this flux? Well, you have 3 options. First, you can make the magnetic field itself stronger or weaker. Second, you can change the area of the loop. Maybe you can squeeze it or stretch it. Or third, you can just rotate the loop, which changes its angle with the field. Any of these 3 things will change the flux. And now for the final step. Step 3. The moment you start changing that flux, an EMF, a voltage, is created. And the faster you change the flux, the bigger the voltage you get. Let's make this concrete with a super small calculation. Just imagine we have a magnetic field of 0.5 Tesla.
and we place a small wire loop in it, which has an area of 0.02 square meters. For now, let's say the field is passing straight through it, perfectly perpendicular. The question is very simple. What is the magnetic flux right at this moment?
The formula is very straightforward, especially in this simple case. Flux, which we write with the symbol phi, is just B multiplied by A. So we just multiply them. 0.5 times 0.02, which gives us 0.01. And the unit for magnetic flux is called the Weber, which we write as WB. So the answer is 0.01 Webers. Easy, right?
But, and this is the main point, remember this number itself doesn't give you any current. This 0.01 Web is just a snapshot. It's like a photo taken at one moment in time. It's just telling you what the situation is right now. To get a current, this value must change. If 1 second later, this value becomes 0.02, or maybe it becomes 0, that change is what creates the EMF and the current.
Now, let's talk about something very, very important for your exams. I see so many students lose easy marks because of one simple misunderstanding. So let's look at these common traps so that you don't make the same mistake.
Please look at this slide very carefully. On the left is the wrong idea that so many people have. They think if I use a very strong magnet, I will get a big current. This is completely 100% wrong. The correct idea is on the right. It doesn't matter how strong or weak the field is, if the magnetic flux is constant. If it is not changing, the induced current will be 0. A steady field does absolutely nothing.
So please, here is a golden rule for your exams. Just burn this sentence into your brain. If you want, say it out loud with me. No change in flux, no current in the circuit. If you remember this one line, I promise you, you will be safe from so many tricky conceptual questions.
Excellent work, everyone. We are at our final section. Let's just quickly connect all the dots and create a very short summary for your last-minute revision.
Just think about how beautiful this idea is. In the last few chapters, what did you learn? You learned that an electric current can create a magnetic field around it. And today, what are you learning? That a changing magnetic field can create an electric current. It's like it completes the circle. It shows the beautiful symmetry between electricity and magnetism. And this idea is the foundation for Faraday's laws, for generators, for transformers, everything that's coming next.
So let's do a quick summary. Point number 1. Electromagnetic induction is nothing but producing an EMF by changing the magnetic flux. Point number 2, the most important word, the key trigger, is change, not just having a magnetic field. Point number 3, how can you change it? 3 ways. Change the field, change the area, or change the angle. And finally, point number 4, this simple principle is the basis for all the electric generators that power our entire world.
And finally, I'll leave you with a small question to think about. We know the secret now is change. So get practical. If I give you one simple bar magnet and one wire loop, can you think of 3 different ways to physically move them to create that change in flux and get a current? Give it a thought. If you can answer this, it means you have truly understood today's lesson. We will discuss the answer in our next class.